Picture an autonomous agent that has been chatting with you for months. It knows you're vegetarian, that your cat's name is Charlie, that you moved from Paris to London last summer. Now imagine asking it a simple question that requires stitching together three of those facts from conversations that happened weeks apart. Under the hood, something has to store all that history, decide what's worth keeping, resolve contradictions when facts change, and pull the right pieces back at the right moment. That something is agent memory, and it has quietly grown from a simple retrieval trick into a full-blown data management system. The question this paper asks is deceptively sharp. Are we actually ready to treat agent memory as a first-class system, or are we still evaluating it like a black box? The motivation here comes from a real fragmentation problem. Over the last 2 years, more than a dozen agent memory systems have appeared, each with wildly different architectures. Some, like Memory Bank, keep a time-stamped stream of experiences and periodically summarize them into reflections, almost like a diary that gets reread and condensed. Others, like MemGPT, borrow ideas from operating systems, splitting memory into a small, fast tier that lives in the context window and a large, slow tier in archival storage, with explicit promotion and eviction between them. A third family, including ZEP and MemRO in its graph mode, represents everything as a temporal knowledge graph, where entities and relationships have validity intervals and conflicts can be resolved by invalidating old edges. And a fourth family goes fully hybrid, routing different kinds of memory objects into different backends, mixing vector search, keyword search, and graph traversal under one roof. The trouble is that prior benchmarks judge these very different systems by end-to-end scores like F1 or BLO on a handful of conversational tasks, which tells you almost nothing about where a system actually breaks. It's like grading a database purely on whether users are happy, without ever measuring latency, index size, or update consistency. The authors respond by decomposing every agent memory system into 4 modules and studying each one independently. The first module is representation and storage, which asks how memory is logically shaped and physically kept. Logically, memory can be flat token sequences, dense vectors, tree hierarchies where leaves hold raw facts and ancestors hold summaries, temporal knowledge graphs, or composite objects that bundle text, embeddings, and metadata together. Physically, it might live entirely in the context window as a transient register, in a single specialized store like a vector database, or across a heterogeneous mix of engines. The second module is extraction, which is the write-time pipeline that turns raw dialogue into memory. This ranges from just concatenating turns, to schema-free extraction of standalone facts, to schema-constrained extraction that forces the language model to emit typed triplets like Kim lives in Paris. The third module is retrieval and routing, spanning native attention over the context, dense nearest neighbor search, subgraph traversal, agentic routing where the language model itself decides what to query, and multi-stage hybrid pipelines that combine several of these. The fourth module is maintenance, covering conflict resolution through time-stamped versioning, capacity-driven eviction using either hard rules like first and first out or soft scores like a heat metric, and language model-driven consolidation that merges redundant facts into denser summaries. With this decomposition in hand, the authors run 12 representative memory systems plus 2 baselines, a long context prompt, and a plain embedding retrieval augmented generation setup, across 11 datasets covering long conversations, multi-session recall, and stateful database execution. The results are refreshingly nuanced. No single architecture wins everywhere. Graph-based systems like ZEP and Cogni dominate when the task is to reconnect facts across many sessions, because their explicit temporal edges let them aggregate scattered evidence. Hybrid filtered systems like MemOS and MemoryOS win on long but coherent dialogues, because course-defined routing narrows attention before the final answer. And on stateful workloads like database benchmarks, the humble long context baseline and memo chat come out ahead because preserving the raw execution trace matters more than any clever abstraction. The takeaway is that memory design should match the workload bottleneck. Think of it like choosing between a filing cabinet, a flowchart, and a transcript. Each is optimal for a different kind of question, and forcing all 3 tasks into one representation costs you. The retrieval fidelity experiments produce one of the more striking findings. Simple Mem achieves the highest recall at rank 1, meaning it's very good at surfacing the single most relevant memory immediately. But AMEM and MemTree crush it at recall at rank 5 or 10, and they degrade far more gracefully when the supporting evidence is many sessions old. In other words, being good at top 1 ranking is a different skill from being good at assembling a complete evidence set. And workloads that require distant or scattered support reward systems that organize memory as a structured evidence space rather than a flat similarity cache. On dynamic updates, graph-based systems handle fact revisions most reliably, while append-only stores and naive fact extraction plugins tend to return stale information, what the authors nicely call hallucinations of the past. And crucially, when they swap the underlying language model across 4 backbones from Qwen 3 8B up to GPT 5.4, the ranking of memory systems barely changes. Stronger models improve answer phrasing after the right evidence has been retrieved, but they can't rescue a memory system that failed to ground the query in the first place. Evidence localization is settled before generation even begins. The cost analysis is where the paper's systems perspective really pays off. Highly structured systems like Cogni and Zep achieve top-tier utility, above 84 on the normalized scale, but only after paying over 100 seconds of average operation latency per query. LightMem and MemTree sit on a far more efficient frontier, delivering strong utility at a fraction of the cost. The underlying rule the authors extract is that operational efficiency is governed by the scope of maintenance, not by whether structure exists. Path local updates in a tree or bounded compression over segments keep costs manageable. Graph-wide consolidation, multi-store synchronization, or repeated whole memory rewriting scale badly as the corpus grows. Localized maintenance is the cost-efficient default. Global reorganization is the expensive luxury. The fine-grained ablations sharpen several counterintuitive lessons. On representation, keeping raw user text beats aggressive summarization and even light compression when the task requires exact detail recovery. Deeper trees help access but cannot recover information that was thrown away during writing. On extraction, coverage-preserving strategies beat highly selective ones. Fast, permissive memorization in MemOS destroys careful, fine memorization on multi-hop reasoning by a huge margin, because fine extraction discards the context needed to connect facts later. On retrieval, explicit query planning and balanced hybrid fusion beat both pure sparse matching and additional reflection stages. The general pattern is that discarding information is far more dangerous than keeping too much, and that light structural guidance beats heavy semantic surgery. Now for the limitations the authors are somewhat quiet about. The workloads are still dominated by conversational and question-answering scenarios, so we do not yet see how these systems behave under truly heterogeneous agent traces with tool calls, multimodal inputs, and long-running plans. The evaluation of dynamic updates uses relatively clean revision patterns, whereas real deployments involve messy partial contradictions and slow-drifting user preferences. And the notion of cost here is dominated by construction and query latency, without deeply modeling storage growth, index maintenance under high write throughput, or multi-tenant isolation. The broader open question the paper points toward is what an agent-native memory system would even look like, meaning one designed from the ground up around semantic access, uncertain and conflicting writes, heterogeneous granularity, and hybrid execution, rather than one that bolts these properties onto existing vector or graph stores. Now let's walk through some questions you might have after hearing all of this. Why does no single memory architecture dominate across all workloads? The core reason is that different tasks stress different parts of the memory lifecycle. Multi-session reasoning stresses evidence assembly across time, which rewards graph or temporal structure. Long, coherent dialogues stress precise grounding within a large but connected space, which rewards course-defined filtering, and stateful execution stresses fidelity to the exact operational trace, where any abstraction can silently discard the fact that will matter later. When your representation happens to match the workload bottleneck, you win. When it doesn't, no amount of retrieval cleverness fully compensates. Why does aggressive extraction hurt multi-hop reasoning even when it looks cleaner? Because extraction is a one-way information filter. When a language model reads a conversation and pulls out crisp typed triplets or short factual statements, it decides what counts as a fact based on the current context, not the future query. Any nuance, hedge, or subtle connector that felt unimportant at write time is gone forever. For single-hop factual recall, this is fine because the extracted fact is the answer. For multi-hop reasoning, you often need the connective tissue between facts, and once that's discarded, no downstream retriever or model can reconstruct it. This is why the paper repeatedly finds that keeping more raw content and letting retrieval do the selective work is safer than making writes selective. If graph-based systems handle updates so well, why aren't they the obvious choice? Two reasons. First, they carry heavy operational cost, both at ingestion, where entities and relations must be extracted and disambiguated, and at query time, where traversal and cross-encoder re-ranking add latency measured in tens or hundreds of seconds per query. Second, they excel specifically at single-hop factual recall and revision, but they can struggle with temporal reasoning and with long, coherent narratives where the important structure isn't captured cleanly by entity-relation triplets. So, graphs are the right tool when your workload really is about entities and their evolving states. But they are not a universal upgrade. For large-scale recommendation systems, the ideas in this paper map surprisingly directly onto some very real production headaches. User modeling for a platform serving hundreds of millions of users is essentially a long-horizon memory problem. You're accumulating years of interactions, preferences that drift, and occasional sharp revisions like a user suddenly switching interests or life stages. The paper's finding that graph-organized memory with explicit temporal validity handles updates most reliably suggests treating user state less as a rolling embedding and more as a versioned entity graph, where preferences carry validity intervals and older signals can be logically invalidated without being physically deleted. That would let ranking models distinguish a stale preference from a current one, which flat embedding user towers routinely conflate. The cost lesson is equally important. In candidate retrieval, where you must serve requests in milliseconds, the paper's rule that localized maintenance beats global reorganization argues for path-local or segment-local user memory updates, rather than nightly full recomputations of user embeddings, and for hybrid indexes that combine cheap dense recall for the head of the distribution with structured filtering for high-value or freshness-sensitive slices. More broadly, the paper's decomposition into representation, extraction, retrieval, and maintenance offers a useful audit framework for recommendation stacks. Most production systems today are strong on retrieval and weak on explicit maintenance and conflict resolution, which shows up as recommendation drift, stale personalization, and the occasional embarrassing recommendation based on behavior the user has clearly moved past. Borrowing the timestamp-based multi-versioning idea and the conservative consolidation as default lesson could give ranking systems a principled way to decay old signals without losing the ability to answer questions like, what did this user care about 6 months ago? Which matters for both long-term value modeling and for regulated domains that require auditability of why a given item was recommended.